All right, if you guys can turn to page 13. So let me recap what we did on page 12. At the bottom of page 12, we talked about how we can go through and decide whether a function is discontinuous and what type of discontinuity, even without looking at the graph. And we're able to just go through continuity condition step by step and decide whichever condition that failed, we know what type of discontinuity we're dealing with. If the second condition fails, we know it must be a non-removable discontinuity. If the second condition passes, but third one fails, we know there's a hole in the graph. We know there must be a removable discontinuity. Okay. And we're able to do that without even looking at the graph and just relying on these three conditions and the function. So I have two more examples that I want to show you involving continuity conditions, but specifically for piecewise functions, because those look a little bit more complicated. Okay, so if you guys can turn to page 13, this is one type, but I'm actually going to circle back to this one because this one I feel like is a more complicated one. And let me show you the first type. And I put it on a worksheet that is attached in later pages. So actually, can you guys go to page 19, actually? Page 19, we'll do a continuity condition problem specifically for this piece one. Okay, so you guys can go to page 19. And let me review and highlight continuity conditions again, and we're going to step through them for our problem here. So first thing is, we got to decide, does a point exist? We got to first identify the c-value. Sometimes the c-value is not given to you explicitly. Well, it's not stated explicitly, but you have to. But there's something enough in the problem to help us find that starting point, that point that we're concerned about. So first thing is establish whether the point exists. Now, if the point doesn't exist, we know the function is not continuous, but we're still going to move on. We're still going to test the second condition because we don't know which category of discontinuity we're dealing with yet. Okay, so think of the first condition as just information gathering. We're never going to stop after the first one. We're going to keep going. Second condition is, does the limit exist? Now, if you're dealing with just one function, you can just find the limit of that one function, and great, you can find whether the limit exists or not. However, if we have two separate functions on either side of our target, we're going to have to rely on one side of it. Okay? And we're going to see some of that with our piecewise function. Either case, we come to the conclusion whether the limit exists or not. If it doesn't, we stop and we know what type of discontinuity we're dealing with. But if it does pass, then we go to the third condition. And third condition, all we do is we look back at the first and second conditions. We look at the results that we got, and we see if they agree with each other. If they agree with each other, then great. Third condition passes. If third condition passes, that means all three conditions have passed. We know the function is continuous. But if the third condition fails because these two are not in agreement, then we can also stop and say that this must be a removable discontinuity. So let's look at number 5 here. Use continuity conditions to show that the function is discontinuous at a point and state the reason for discontinuity. Then determine if the discontinuity is removable or non-removable and state why. Okay, so the first thing is we got to test the point, find the point. But the c-value is not stated explicitly. So if you had to guess, what do you think the C value is? 3, yeah. So that's where the point in question is. We know that we have two graphs. They are meeting up at 3, but we don't know whether it is connected or whether they're disconnected. Okay, but we do know that that's the point in question. Our C value is 3. Okay, so first thing is identify f of 3. We need to find that point, right? I'm just taking my first condition and replacing C with 3. All right, so we have two functions to choose from. How do we know which one to use for f of 3? Bottom one, because there's equal, right? The second function defines 3 because they see the equal sign. The first one doesn't because it's only involving less than 3. So we insert 3 into the second expression. -9 plus 12 minus 2. What do we get? Right, we get 1. All right, second condition. Does the limit exist? All right, can we rely on just one limit statement to determine the limit? No. The reason why we have two separate functions and we have to involve both of them. And anytime you want to have to involve both expressions, because we have different ones approaching from different sides of 3, we have to go through one side of the limit. Okay, so I'm going to copy down exactly as I see here. I'm going to replace C with 3, and I'm going to determine which one is appropriate for the one-sided limit. Okay, so I'll start with the limit as x approaches 3 from the right side of 3. So which expression is for the right side of 3? The second one, because if you think about 3 positive, that just means values greater than 3. So 3.1 or 3.5, 3.6. Those are all values greater than 3. So let's copy down the second one here. And separately, we also need to find the limit coming from the other side. The left side of 3, so these are values less than 3, like 2.5, 2.6, 2.7. Those are all values less than 3, so we know that the first one is the one that's appropriate for approaching 3 from the left side of 3. So now we're going to evaluate both of these one-sided limits, but you're just going to plug in that whole number. Okay? Don't worry about that plus or minus. That's just for notation purposes for now. So we're going to evaluate the limit at those x values. So -3 squared plus 4 times 3 minus 2, it's going to end up being the same as the top of the right one. Second one-sided limit approaching 3 from the left side of 3. 9 minus 12 plus 6. What does that equal to? 3. Okay, what can we conclude? Limit, okay, therefore, the limit does not exist. Okay, so we don't have to say that we don't have to write out the statement and say that they don't equal to each other. We can look at that and just make that conclusion. So we can say, but we do need to make a conclusion. So we say limit as x approaches 3. We don't have to write out this whole piecewise function. We can just label it as f of x, but do make sure that you include f of x as appropriate notation, and we say that this does not exist. Okay, good with second condition. All right, what happens next? Do we keep going? Do we go to the third condition? No, we only go to the third condition if the second one gives us a number, gives us, it does pass. So what type of, what conclusion can we make? There must be a break in the graph here. Make sure you specify the location at x equals 3. All right, does this process make sense?
Yes.
So can you guys practice the same process for number 6? It's going to feel very similar. I just want us to get that extra practice so that we feel good about this type of piecewise function, and then I'll talk about the other type. Make sure you include all these little notations. So I want to see every little piece that you notice how similar everything that we write is with the original, with the continuity condition, right? Really, the only thing that you're replacing is you're replacing the C, you're replacing the f of x, and then you're actually finding those values that they exist. But all of those notations are all in our process, right? We don't want to do any kind of shorthand. We want to write it out the way that's presented. Okay, so very similar thing with number 5. There's a point. You're going to have to choose which piecewise function to use. There are 2 different functions split on either side of 1. So we're going to do limit as x approaches 1 from the left side of 1, limit as x approaches 1 from the right side of 1. You pick the appropriate function for each limit statement. We find those 2 limits. They're not going to agree. We say that the full limit does not exist, and we can stop and conclude there must be a non-removable discontinuity at x equals 1. So pretty much everything that you have on paper should look exactly like mine, right? All right, any questions? I'll leave this up for another few seconds here. If you're good with this, let's go back to page 13 and let's compare and contrast how this piecewise function is different. Page 13. Go ahead and cross off this continuity on the closed interval. We really don't need to go through all that detail. So we're going to use that remaining space for this warm-up problem. I call it a warm-up problem, but really it's something that we haven't quite seen yet. So we're going to kind of explore this from the beginning. Okay, so just some quick observations here. We just did number 5 and 6. What do you notice is different between this piecewise function and the one that we just did?
They're equal signs.
Okay. There are equal signs. Okay. I also want to make this observation here. These are both connected parts of graph, right? If you look at both these, you're going to see that they're both graphs, branches of graphs. So there's a graph here. There's a graph here. Now, visually, can you tell me, or what's your thinking in terms of what each of these will produce with those restrictions on the graph? okay, not a circle. The restriction is going to tell us something about how the graph is going to
Oh,
look.
they're just like points. They're
Okay.
not.
Okay, so the point is for the x plus 5, because why? It's only at one point, right? So if even if x plus 5 is a line, but it's only restricted to one single x value, this second expression is just going to give us a point. It's not going to give us anything more than that. How about the first one? Or what do you think this means?
That point isn't going to be at x equals 2.
Okay. It also, this is saying that we want this graph to exist everywhere except 2. Okay, so this is also a graph. Because we're going to show the entire graph, we're just going to withhold x equals 2. And that is going to be defined elsewhere. Now, this notation looks a little bit more confusing because it doesn't feel as straightforward as this, right? Here you can clearly see I got a graph to the left of 3, I got a graph to the right of 3. But this one is saying the graph is going to be the same on either side of 2, and then there happens to be a point that is defined elsewhere. So this notation does feel a little bit more confusing, but this is the way that it's going to be presented. However, I want to see if I can maybe write it in a different way that can be visually more helpful. Okay. Now, having said that, it will never be written this way in terms of, if you see a problem that has this scenario, it will never be written in the way that I'm going to show you, but I think visually it could help. So to the side, I'm going to have you guys write it this way here. I think it may be helpful to some of you. So this first statement, okay, x squared minus 4 over x minus 2, it exists everywhere except at 2. So I can say that this graph, x squared minus 4 over x minus 2, is going to exist to the left of 2. Right? Everywhere except 2 includes the left of 2. Next up, I do have something that exists at 2, which is the x plus 5. And what about to the right of 2? What do we use for to the right of 2? Yep, also the first one. So I think this visually may be more helpful because we can clearly see, okay, I got a graph to the left of 2, I got something defined for 2, and I have a graph to the right of 2. But all I did was I just copied down the same function to the left and to the right of 2. So basically, rather than writing it out this way, they're going to write it this way. But I want to make sure that we understand this is basically the same thing as this. So if you see this problem, you can always write it out this way if you want, and then step through continuity conditions that way, if that makes it feel more clear. But let's work at it from this perspective, since we see everything clearly in front of us, we see everything laid out. Right? So let's go through our continuity conditions. Okay. What's our C value? 2, right? We can clearly see that is where the graph may be experiencing some issues because you have different values all over the place and we don't know if they're all lined up. Okay, so f of 2, what do we use for f of 2? The middle one, right? Okay, second condition, does the limit exist? Now, can we rely on one limit statement or do we need 2 limit statements?
2.
Okay, so the answer is you can use 2, but we only need 1. Why do you think that? I mean, it's not wrong if we do one side limit, but why do you think we won't really need it. They're the same, right? It's the same. So, I mean, I can do it, but it just feels like extraneous work doing the same thing twice. So if I have the same function to the left and to the right of 2, then I can just merge that together and just do one limit statement. Now, if you did one-sided limit, it's not wrong. You can do them twice. You would come to the same results. But I'm just going to do one. So now this is a limit algebraic problem that we have to kind of go through our steps. All right, what's the first thing? Plug in, right? No factoring. We don't do any of that until we take care of our first step. Okay, so 2, insert it in for x. What do we get? Say again? 0 over 0. Okay, so that's the green light for us to keep going, right? So now we know there's a hole. We know that there is a limit that exists. Now we can look for it. Right, what's the factor form for x squared minus 4? 2x minus 2. All right, do you see the hole? Yes. Remove. Reevaluate. What do we get? 4. Okay, do we keep going?
Not equal.
Wait, but does the second condition pass?
Yes.
It does. Okay, so I see where you're getting at. You already know what's going to happen with the next condition. But I just want to specify that we do go to the third condition, right? Because we do have a limit. Okay, now that we're in the third condition, we look back and what's your conclusion? Are the first 2 conditions in agreement? They're not, okay? So we're gonna write it out that way, okay? So you're gonna copy down your third condition, everything the same as you see here. The only thing you're gonna replace is what? The C value. So you're gonna copy down and instead of equal sign, you'll just put doesn't equal to. Okay, what's our conclusion here? Wait, what type of? Removable, right? There's a hole in the graph. The limit exists, the point just doesn't line up with the hole. So this is a removable discontinuity. Okay, so we're almost done with this problem. It's asking if it is removable. It is, right? We are able to justify that. And if it is, redefine f of 2 to make the function continuous. So we know that if there's a hole in the graph, there's only one thing that's preventing it from being continuous. So what can we do with f of 2 so that we can redefine it to make it so that it is continuous? Yeah, we just fill in, because right now that hole is not being filled, right? That point is somewhere else. So if we redefine f of 2 to be equal to 4, then we can fill in that hole. So we redefine f of 2 equals 4. So basically, we rewrite that first statement to allow for that hole to be filled in. So if it is truly a removable discontinuity, we should only be able to, all it takes is that one minor adjustment. It's only 1 point away from achieving continuities. Okay. You're gonna see some of this in your homework. the variables in the problem homework may feel a little strange, but so just try your best, work through it, step through continuity conditions. If you're stuck, it's okay. We can revisit that tomorrow. Okay, but any questions so far, though? All right, so one more topic to go over. This is the intermediate value theorem. Okay, let me read the definition and then try to make it so that hopefully you can understand. Because sometimes the wording here is a little bit convoluted. So this is intermediate value theorem, IVT, as abbreviation here. So IVT says if our function is continuous, so that's an important statement. We cannot move forward if we cannot confirm that the function is continuous on the closed interval. So there can't be any holes or asymptotes. If there is, we can't make these conclusions with such limited information. So if our function is continuous on a closed interval and k is any number between f of a and f of b, then there is at least one number c in the closed interval such that f of c equals k. Okay, so it's kind of hard to understand. Let me reword it a different way. If a function is continuous, okay, then the graph is guaranteed to touch all the y values between the two endpoints. So let me say it this way. Let's say one endpoint starts off at a y value of 5. Okay, and then we know it's continuous, and then it ends up at a y value of 1. Okay, let's say that's all you knew, and you didn't quite see the graph in front of you, but you kind of have this idea of what it could look like. Can I guarantee that there is some k value such that the y is equal to, let me just choose a random decimal here, 2.96? Can you convince yourself, can you guarantee that this graph is going to hit 2.96 somewhere along the way? Yes, right? And the reason why is because if you start off at a value above 2.96 and end up at a value below 2.96, the graph has to touch every y value in between because we've already established the function is continuous. So that's what that's all IVT is saying. It's saying if I want to prove or if I want to guarantee a specific value, first establish the function is continuous. Next, establish that one endpoint is sitting above or below. And then the other endpoint is on the other side. Okay. We just want to know, we just want to have our endpoints on either side of our target because the graph has to cross through at least once. Okay. And we're making these conclusions without the use of a graph. So obviously, if you have the graph in front of you, you wouldn't need IVT, but we're trying to make this conclusion with, the minimal information possible. So I can guarantee this y value as long as you tell me that the graph is continuous and one endpoint is below and the other endpoint is above, then I can guarantee that there's any y value that you want between those two will be reached. Okay, does that make sense? Okay. All right, so let's look at example 1 and see if we can work through this process. All right, so it says use IVT to show that there is a 0. So let me talk about what that means. That is a y value. So that's our target. I want to guarantee a y value of 0 somewhere along the graph. On the interval from 0 to 1, so this is important that we understand these are not y values, these are x values. So we never want to be comparing this with these two, okay, because these are matching variables. We want to compare y values with y values. All right, so first thing is we need to establish the function is continuous. The nice thing here is this is a polynomial. No variables in the denominator. And polynomials are safe. There are no asymptotes, there's no holes, there's no breaks. We don't do any tests. We just know that we're guaranteed to have a continuous function. So we want to practice writing out those conditions. F of x is continuous. Now, f of x is continuous everywhere because it's a polynomial, but we just want to specify the condition, the endpoints or interval. We only care about the interval, so we're only going to establish that continuity statement for our interval. Okay, so our first condition is good. We know that we don't have to worry about any potential breaks in the graph. We've already established the function is continuous. So now we want to look for our y values, right? We want a y value above 0 and another y value below 0. So let's find those y values. I have my endpoints. So I'll insert each endpoint into the function and look at their y values. So f of 0, if I insert 0 in for x, what do we get?
-1.
-1. So we have a y value below our target. So therefore, we want the other endpoint to be what? Above, right? If we don't get one below and one above, then we really need more information, right? But if we're just limiting ourselves to just these information, then we need a one below and one above. Otherwise, we just don't know exactly what's happening. All right, so same thing. Let's insert 1 into the function. What do we get? 2. Or can we guarantee a y value of 0?
Yes.
Yes. Okay, so this is what we're looking for. We're always comparing. These are the numbers we're looking at. We want this number to be between the y values that we gathered. Now, we don't know exactly where it's going to happen. We don't know the x value, but we know somewhere between is gonna be able to be reached. So for the next example, we're actually going to find that y value or find that location, that order pair where this target is reached. And if we were to find that order pair, we should replace y with 0 and solve for x, but we'll do that next one. Okay. Now, let's justify. We need to be able to finish off our statement. So we'll say this, by IVT, since, okay, and we've already established the function is continuous, so we don't have to restate that. By IVT, since. Now, there are different ways to write this, but this is the most efficient way that the College Board has used for grading. So I'll write it this way. Since f of 0 is equal to -1, and -1 is lower than our target of 0, and 0 sits between -1 and our upper target, which is 2, and 2 is coming from our other endpoint, then so justification can be a little wordy. I think this is the way to write it so that you can get all the information across, and they'll take it and they'll see all the that you understand all the different pieces involved. So we know that we're comparing our target between our two endpoints, and we can establish that relationship. And then we're also identifying that those two endpoints, those y values are coming from the endpoints. Any questions here? So again, we just know that there is a y value of 0, but we haven't established where it is yet. And the next question, we're going to go one step further and actually find the physical location, physical order pair, where these behaviors occur, or where these guaranteed points occur. Okay, so let's go to page 14, and we'll do one more example. Okay, example 2. Verify that IVT applies for our function on the interval from 5/2 to 4. Let me write that a different way. 5/2 is 2.5, so we're going from 2.5 to 4. For f of c equals 6 and find the c value. Okay, so first things first, what's our target?
6.
6. We want to guarantee this y value of 6. So the big picture is we're going to insert 2.5 and 4 into the function, and what are we looking for?
One higher, one lower.
Good. One higher than 6 and one lower than 6. Right? That's all we need. Good. But there is another thing we got to worry about. That is the issue of continuity. Okay. Our function, this is not a polynomial, and we gotta look a little bit more, we got to pay a bit more attention. Because the polynomials, you can just look at it and just say, okay, it's continuous, I don't have to worry about it. But this one, what do we have to at least look at and pay attention to? Is there a potential discontinuity in our function? Okay. How can we locate a potential discontinuity on our graph? Where do we look? Denominator. Good, denominator. Because whatever makes the denominator 0 is a break in the graph, right? So what do you notice? This is a vertical asymptote because there is no x minus 1 to pair up and cancel in the numerator. So if I set x minus 1 equal to 0, I get x equals 1. There's a vertical asymptote at x equals 1. So we know there's a break. Now, just because there's a break in the graph, does that mean that we're going to fail the continuity condition? Okay. Why? Okay. We don't care if the entire function is continuous, right? We only care about what? 2.1. That's right. We only care about the interval, right? So as long as your interval is protected, it doesn't matter if there's a break outside that interval. So there's only one break in the graph, and it's at x equals 1. Okay. Is this one going to impact our interval? It's not. It's not, right. That break is safely outside the interval. So is our interval safe?
Yes.
Yes. So this is the only point you got to worry about, right? There's no other discontinuity from our function, and it did not impact our interval. So now we can say our function is continuous on the interval, on the closed interval. Okay. I'm doing 2.5. It's just easier thing for students to recognize rather than 5/2. Okay. Okay, so we got that condition out of the way. We tested it. We're safe. We can continue moving forward. Now, let's say there was a break in our interval. If there was a break in the interval, then the function is not continuous on the closed interval. Then we just stop the problem and say IVT doesn't apply. Right? We cannot move forward with IVT if there's a break in the graph because we don't have the graph in front of us. We're really relying on that continuity condition to help us guarantee. If we don't have that guarantee, then there's too many variables or too many issues. We can't make that guarantee anymore.
So if it were like x minus 3, then we couldn't make the guarantee anymore?
Exactly. If it was x minus 3, then if the vertical asymptote at 3, if your interval is ever compromised, we can't move forward with our problem. We're going to see that with other theorems as well. Yeah, we got to get that first condition passed. If it doesn't pass the first condition, the rest of the problem doesn't apply, right? We can't do anything unless that first condition has passed. Okay, so we're good with the first condition. And now we can move on to testing our endpoints, right? So one at a time, we'll insert endpoint into each endpoint into the function. Now, you may not have a calculator. That's okay. I'll do all the calculations for you and just write this down. Okay, so all I'm doing is inserting 2.5 in for the x of the function. And numerically, that's going to come out to be 5.8. So is this above or below 6? below 6, right? So that means we need 4 to produce what?
Something
Something
higher.
higher, right? We need one lower and one higher. Okay, otherwise we don't have enough information. Okay, F of 4. So numerically, that's going to give us 6.7. And we guarantee a y value of 6.
Yes.
Yes. Okay, we start at 5.8, we end up at 6.7. We know there are no accidental breaks along the interval. We're guaranteed that somewhere along this path, the graph is going to hit and touch y value of 6 at least once. Okay, so let's make our conclusion, but then there's one more thing we got to do after that. But let's write our conclusion first. Okay, the same setup as previous. We identify the fact that we are testing endpoints, and the result of those endpoints do end up giving us a value above and below our target. And we've established continuity. So in that brief statement, we're able to show everything that justifies our understanding of IVT. Okay, so what is it about this problem that we have to go further with? Solve for C. So in other words, we need to find the order pair. We need to find the X value, right? We know the Y value is 6, but we don't know where those exact points are. So how do you think we can do that? What can we?
Yeah, you said it equal to 6.
Yep. So we can replace 6 in for Y, solve for X. Do that. We have the Y value. We're just now looking for the X on the graph. I'm going to force this into a fraction and cross multiply here. Okay, what do you think we need to do next? Set everything equals 0, right? We got X squared, we got X, we got a constant, we got a factor here. We got to bring everything over to one side. Factor multiplies to be 6, adds it to be -5. All numbers. Yeah, -6 and 1 is not going to quite do it because I need a +6 with the 2 multipliers.
-2 and -3.
-2 and -3. Okay. We have two X values, 2 and 3. So we have potentially 2 C values. So we have 2 order pairs where the graph actually hits a Y value of 6, order pair 2, 6, and order pair 3, 6. But are both valid solutions for our problem? Okay. I mean, these are physical order pairs that has a Y value of 6, but what do we have to consider? Good. We go back to the interval, right? If something is outside our interval, it's not part of our problem. If it's not part of our problem, we're gonna remove it. So which is not part of our problem? The two. Now, once you get past this point, once you get past point A, you should always get a real number solution. Okay, we're never gonna get past point A and then realize that there's no solution. You're gonna get at least one solution, but if there's more than one, you gotta look into the fact that maybe not all of them can fit. Okay, guys, we'll pick up tomorrow. You guys have homework. Finish the ones that skipped over yesterday. Go up and get your phones. We have 2 more sections to go over for chapter 1, and then we're gonna get ready for a review of our test. Yeah, so if it's not equal to 0, that means there's a break. And then wherever the break in the graph is, you're gonna compare that with interval squares here. If it impacts the interval, it's then if it's not, if it does not, then